Alright, supercontingency man here. Today we're going to talk about the quantum Zeno effect and a possible explanation from it from the supercontingent interpretation of quantum mechanics. Now, in this interpretation, I'm not quite sure if the wave function of the system is objective or it's subjective, but today we're going to treat it like it's objective. Alright. If you consider the wave function, which is denoted by the symbol, then it looks something like this. It's all, screwy and, with respect to the wave function itself. And we're going to have a system today of radioactive decay. Now, for simplicity, I've made the wave function into a regular sine function. Now, this is to show the localization from adding or taking away eigenvalues from the system. And at this point, it's in a superposition of both eigenstates. And there's superposition for you. And this is part of supercontingency. Now, we show that as we remove or take or add eigenvalues, that it becomes extremely more and more localized. And as time goes on, you can see it getting more and more localized. I'm bad at drawing, sorry. Until it reaches something like this. Now, at this point, we're going to open the box. And, because this is like Schrodinger's cat experiment, we're going to open the box to see if the cat is dead or alive, because at the moment, it's in a superposition of both states. It's both dead and alive. So when we open the box, it's going to fall back to its ground state, and either be A, it's going to be dead, or B, or A, it's going to be alive, or B, it's going to be dead. Now, if it's shown with experimental data that if we make repeated observations quickly enough of a system, that it will remain as the initial observation. Take, for example, radioactive decay. If we make these observations quickly enough and often enough, then it will never decay. So, with the cycle, the probability that it will be decayed or move towards state A, or move towards state B, is 0%. That means it has a 0% probability of becoming decayed. That's only if it's quickly enough. So, because as time goes on, it becomes extremely more localized, the wave function does. And since time goes on, the probability that the particle will be decayed tends toward 50%, or we think it does. Either it tends toward 50% or it tends towards 100%, but since we don't know what state the system will be in, we just say 50% because it'll be decayed or not decayed. We can infer, this is the explanation, my explanation of the quantum Zeno effect, that because we are making repeated observations quickly enough, it doesn't have enough time to reach a certain state where it can actually fall and have a 50% chance of decaying. Until it reaches that 50%, it has no chance of decaying. It always stays at 0%. So I can infer that there is a certain threshold right there that if it surpasses, there will be a 50% chance of it decaying and a 50% chance of it not being decayed. And this time, I propose, will be the, okay, well, anyway. But until then, it has, if we make those repeated observations quickly enough, it has a 100% chance of not being decayed. And 0, of course, of being decayed. Because we are making those observations quickly enough. Now, whether or not this grows at a certain rate is dependent upon the environmental factors. And that's why when some of them are in large groups, they kind of communicate with each other
through quantum entanglement. And through this explanation of the quantum Zeno effect, it does not violate any EPR laws, and it remains that information cannot travel faster than the speed of light. So, if we consider the system, if we measure it quickly enough, it will continually fall back to the ground state, build, and then if we measure it before it reaches that certain state, where the chance that it will be 50%, if we measure it before that, it will fall back to its ground state and never really have the time to decay. But if we wait long enough, and wait for it to reach above that ground state or at that ground state, say it's here, then there will be a 50% chance in that margin or above that it will be decayed. So that's it. Well, thanks for watching.